What we've depicted here is part of some path C, which can be parameterized by x equals x of t, y equals y of t, a less than or equal to t, less than or equal to b. So, in other words, simply a path that we can parameterize in the usual manner. Then, at any point along this path, we have a tangent vector, and that tangent vector can be given by simply x prime I plus y prime j. Now, this is nothing that you're not pretty familiar with by this point. Just kind of reviewing where we are and also motivating what's going to end up being a normal derivative, a derivative of flux normal to a surface. And we've talked about that a little bit. We want to get a handle on how that works. So we have a curve. We have an expression for our unit tangent, for our tangent vector, and we can of course make that into a unit tangent vector. We simply have to divide the tangent vector by its magnitude, and that might be a little small and hard to read, but it's the usual expression, x prime I plus y prime j divided by the square root of x prime squared plus y prime squared. Now, if x prime I plus y prime j is a unit vector, then y prime I minus x prime j is normal. We've simply reversed the coordinates and made one of them negative, which gives us a vector whose line has a slope equal to the negative reciprocal of the slope of this line, so that we do have a right angle here. This vector is then normal to the curve. And we can verify that also by just taking the dot product. We get x prime y prime minus y prime x prime. We get 0. Now we want to really grab onto the unit normal, which is going to just be our normal vector divided by its magnitude. That's going to be y prime I minus x prime j divided by the square root of x prime squared plus y prime squared. Now we know that our function f of x, y, if we have a vector function f of x, y equal to mi plus nj, then the integral of f dot ds is the integral of the component of f parallel to the curve multiplied by our distance along the curve. And that integral can be written in complete notation as f being mi plus nj. We write m at x of t, y of t, I, plus n evaluated at x of t, y of t, j, just to make the t dependence specific. If we have a parameterization and we have the vector function, then the value of t gives us our values of x and y, which we plug in to get our values of m and n, giving us this expression for our vector function. We dot that with our ds vector, our incremental displacement vector, which is just equal to x prime of ti plus y prime of tj, which is a tangent vector, multiplied by dt. That gives us the unit vector multiplied by the magnitude of the derivative vector times dt, again giving us our incremental displacement. A couple of notations here. This incremental displacement, this ds vector, can also be written as unit tangent vector times the ds vector, which is just the ds increment, which is just our distance increment. If we multiply the unit tangent vector by the distance increment, we get the displacement increment. Unit tangent vector, as we've said already, x prime I plus y prime j over the square root of x prime squared plus y prime squared, and ds just being the square root of x prime squared plus y prime squared dt, the magnitude of our derivative vector. If we interpret t as a time parameter, then this is simply our the magnitude of the ds is simply the velocity multiplied by the time increment, which gives us the distance increment. Or, alternatively, in this form, the vector velocity multiplied by the time increment, giving us the vector displacement. Okay, so that with this notation, we could also write this as the integral of f dot t ds, because t ds, vector, unit tangent vector times displacement, the distance increment, gives us our displacement increment. So if ds, vector ds, is replaced by t times scalar ds, this is a result. And returning to our more compact notation, we can say that the integral of f dot t ds is the integral of mx prime dt plus ny prime dt, which is, again, just the integral from a to b of m dx plus n dy, where we understand that a and b are limits on t. And we should really indicate that these are t limits and that this expression is associated with this parameterization. Now, by Green's theorem, we know that this or this, any of these integrals, has to be equal to the double integral with respect to area of negative my plus nx. That is, the integral of m dx plus n dy is equal to the area integral and represents the integral of f dot t ds or f dot vector ds. Now let's think about the integral over c of f dot n ds, which is going to represent the normal component of the force integrated over distance along the integral, along the curve. Recalling that n is just the unit normal y prime I minus x prime j over the square root of x prime squared plus y prime squared, and that the scalar ds is just the square root of x prime squared plus y prime squared dt, we see that n ds, this times ds, is just y prime I minus x prime j. The square roots are one in the denominator, one in the numerator. They divide out, and we just end up with this times dt, which is what we have here. Basically our normal vector times the dt, and then that's dotted with mi plus nj. And that dot product comes out my prime minus nx prime dt, which is going to be the integral. Now let's put our t dependence in there, again our dependence on the parameterization. And that then equals the integral of m dy minus n dx. Since y prime dt is our dy and x prime dx is our x prime dt is our dx, we get this integral, which looks a whole lot like this one, but it's a little bit different. M is now paired up with dy instead of dx. N is paired up with dx rather than dy and is now negative. Now Green's theorem tells us that this integral is equal to this area integral. We identify m as whatever we're multiplying by dx, and whatever's multiplied by dx appears over here with its negative y derivative. Now what is it that appears here with dx? It's now negative n, so that negative n has to appear in this area integral, and it has to be the y derivative of negative n. So we have negative ny, but we have the negative of that because it's the negative y derivative. The y derivative of the coefficient